Okay, the last thing we did was an example where we had f sub omega plus 1 of 3. Now, omega plus 1, if you remember, we can also think of as the natural numbers, 1, 2, 3, 4, 5, blah, 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 in union with one extra element at the end. Now, there's nothing stopping us from adding another element right into here and creating something like omega plus 2. This is completely valid. And it's something that we can also plug in to the fast-growing hierarchy. So let's see what that does. Let's see what that does to the output of the function. So f omega plus 2 of 3. We have a successor. So we're going to recurse this and create 3 copies of the omega plus 1 function, which we can rewrite like this. So f omega plus 1 of f omega plus 1 of f omega plus 1 of 3. Now f omega plus 1 of 3 is something we've already dealt with, and it creates a very, very large output. So instead of just writing this down again, we'll just put large here, because we know this is just a very, very large number. Now what's f omega plus 1 of this number right here? So let's just write down. We'll keep this separate for now, and we'll deal with that later. But f omega plus 1 of some large output here. We have a successor here. So what we do is we recurse this function, and this is going to be equivalent to whatever this large number is, this many copies of the f omega function of this also. So if we were to write that down, we'd have to go f omega of f omega of f omega, blah, 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 blah. And the number of terms we have here is this large number. And how we would evaluate this is we would diagonalize. So we would plug this number into the subscript, evaluate this, and then plug that into the next subscript and the next and the next and the next, all the way down the line, and the total number of arguments being this huge large number. And then we'd have to take this and do the exact same thing with this function too to complete the whole thing. So as you can see, this gets far, far, far beyond omega plus 1. If I have something like, one thing we did last time was a number that was similar to Graham's number, f omega plus 1 of 64. Well, I can totally blow this out of the water with something as, with such a small input as 3 if I just plug it into f omega plus 2. I could put a googolplex into this input right here, and it would still be vastly smaller than just putting a 3 into omega plus 2. And this is where we really have to get used to the idea of where the power of the argument comes from. It's not what you plug into the base here. It's what you plug into here. That's what matters. This is the point that we have to increase if we want to make ever-increasing functions, basically. So we can keep on going from this. There's nothing stopping us from doing omega plus 3, omega plus 4, omega plus 5, blah, 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 blah. And we can even do omega plus omega. This is totally allowed. This would be equivalent to having 2 separate sets of the natural numbers, blah, 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 blah. And I think we did an example of this before. And this truncates to just omega 2. That's another way of writing it. Now this is an important one because it's the second time that we reach something that has a fundamental sequence. Now, if you'll notice, successors do not have a fundamental sequence. There's no way of us writing this down in a single set. Whereas something like omega, we can simply write that as a sequence of things. 1, 2, 3, 4, 5, blah, 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 blah. So now we come upon something that also has a fundamental sequence. So how would we write down omega 2? Well, let's keep it as omega plus omega, because this is the easiest way to kind of visualize it. So omega 2 is equal to omega plus omega. Now, how would we get to this omega here, writing down a sequence of numbers? Well, we do the exact same thing as we did with the regular omega. We go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, up into infinity. Except this time we have the omega in front that we have to add to it. So the fundamental sequence of this is going to be omega plus 1, omega plus 2, omega plus 3, blah, 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 off into infinity. So this is the fundamental sequence of omega 2. So if we want to plug this into the fast-growing hierarchy, let's keep this in mind. So f omega times 2 of 3. Let's break this apart into f omega plus 1 so it's easier to deal with. And then we take the third element of this fundamental sequence. Now, another way of kind of thinking of this without thinking in terms of fundamental sequences is basically you're just breaking this apart so that you get a free omega on the right-hand side here. And then you just turn this omega into whatever you have in here. So that's kind of a quick way of doing it without having to write out the fundamental sequences and whatnot. So we could just do this, and we end up with f omega plus 3 of 3, which is a successor, which we can break apart into 3 copies of omega plus 2. And we know how to deconstruct that from there, so we won't go any further. So omega times 2. We can also do omega times 3. And once again, this is not a successor, so it does have a fundamental sequence. How do we figure it out? Once again, we break it apart. So omega times 2 plus omega. We now have a free omega, and this would be have the fundamental sequence of omega times 2 plus 1, omega times 2 plus 2, omega times 2 plus 3, blah, 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 on and on. And it just keeps going like this. We have omega times 4, omega times 5, blah, 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 and even omega times omega, which truncates to omega squared. And this would have the fundamental sequence if we keep, and let's just keep it as this to visualize it once again, as omega times 1, omega times 2, omega times 3, blah, 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 blah. So if we were to plug this into the fast-growing hierarchy, omega squared, we would break this apart into omega times omega. And we can diagonalize this one directly. We have a free omega on the right-hand side, so this turns into a 3 equals f omega 3. But this time we're not done, because this also has a fundamental sequence. We have to break this apart more. And we've done an example of this already. We've broken apart omega times 3 into omega squared plus omega. So we'll do that. We have f omega, oh sorry, not omega squared, omega times 2 plus omega. We once again have a free omega here, which we can turn into a 3. F omega times 2 plus 3. And we finally have a successor, which we can plug into the fast-growing hierarchy and recursus, and then we can go on from there. So omega squared, we can go on from here to omega cubed, omega to the 4th, omega to the 5th, blah, 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 and even omega to the omega. Now this has a fundamental sequence as well, and it equates to omega to the 1, omega squared, omega cubed, omega to the 4th, blah, 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 blah. So if we were to plug this into the fast-growing hierarchy, we have a free omega here, so we take this element of here, and we turn this into a 3. So we end up getting f omega cubed of 3. This also has a fundamental sequence, so we need to break this apart. So how do we break apart omega cubed? Well, let's turn it into omega squared times omega. And I'm going to do this outside of the hierarchy, just so I don't have to keep on writing on f's and all this and stuff like that. So let's just do this separate of the hierarchy. Break this apart into omega squared times omega. We can change this omega into a 3 because we're diagonalizing. So this ends up being omega squared times 3. So let's keep 2 of the omega squareds, and then we'll break one off. So we have plus omega squared. Then we can break this omega squared up into 2 omegas. So this ends up equaling omega squared 2 plus omega times omega. We have a free omega here that we can turn into a 3. So this equals omega squared times 2 plus omega times 3. Then we can break this up into into omega times 2 plus omega. So we'll do that. Plus omega times 2 plus omega. And finally, we can diagonalize this w into a 3, where we finally have a successor, which is omega squared times 2 plus omega 2 plus 3. and then just for fun, we'll put that into the final thing. So this eventual answer from here after the complete deconstruction would be f sub omega squared times 2 plus omega times 2 plus 3 of 3. And finally, we have a successor here, which we could do 3 copies of this function, except this would be plus 2 here, and we can keep on going in that fashion. And it still doesn't end here. We have omega to the omega. We can also have omega to the omega to the omega, omega to the omega to the omega to the omega, blah, 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 blah. And we can even have an infinite tower of omegas. Believe it or not, that is still allowed. And this has a special name, which is called epsilon naught, which we will deal with in the next video.